From the moment we wake up and swipe a screen to the algorithms tracking global supply chains, our modern lives run entirely on computers. Yet for most of us, these devices are black boxes. We treat our smartphones and laptops like magical glass rectangles that somehow know exactly what we want. But beneath the glass, there is zero magic. There is only a rigid, mechanical logic, operating exactly as it was built to do. Whether tapping a mobile game on a smartwatch or routing a space shuttle through orbit, every computer operates on the exact same continuous four-step cycle. This cycle takes raw, chaotic data from the real world, organizes it, and turns it into structured, useful information. Understanding this four-part cycle is how you begin to see through the complexity of every piece of technology in the digital world. Step 1 is input. Devices like keyboards or sensors capture raw commands and feed them into the system. Step 2 is processing. The CPU acts as the machine's logic engine, calculating and transforming those inputs based on mathematical rules. Step 3 is storage. RAM provides temporary workspace for active tasks, while SSDs lock away data long-term. Step 4 is output. The machine translates logic into formats humans perceive, like pixels on a monitor. But that perfect mechanical cycle is entirely useless on its own. Left to itself, a computer is just dead metal waiting for instructions. That's where software comes in. It's the invisible brain that manages the physical hardware loop and gives the machine a purpose. At the base level, you have system software. Operating systems like Windows, Mac OS, or Linux manage the computer's core resources and tell the hardware how to behave. Sitting on top of that manager is application software. These are the specific tools, like your web browser, video editor, or spreadsheet, that let you actually accomplish a task. It's this marriage of rigid hardware loops and flexible software that allows the same machine to act as a simple calculator one minute and a portal to the world's entire digital library the next. So what happens when you take that four-step universal loop and scale it up? You start with microcomputers, the laptops and PCs designed for individual use. Scale that up slightly, and you get mini-computers, which manage data for entire teams. Push the scale further, and you enter the realm of mainframes. These massive architectural systems handle millions of simultaneous transactions, like processing the global stock market in real time. Beyond those are supercomputers, massive arrays running trillions of calculations every second to sequence human DNA or model global climate systems. Despite the staggering difference in physical footprint, the fundamental input-to-output logic remains identical across every single one. Scaling billions of these loops globally has given us instant connectivity and limitless storage, but it carries a massive hidden cost. Physically, our devices demand constant manufacturing. The resulting electronic waste creates a permanent environmental footprint, while prolonged screen time introduces real health and ergonomic stress. Digitally, massive centralization creates deep vulnerabilities. Putting our organizational and personal data into these systems triggers an everyday battle against data breaches and privacy violations. Our absolute reliance on these scaled machines introduces global friction that we are only just beginning to manage. The next phase of computing is trying to solve these flaws. We are already pushing toward quantum computing and placing artificial intelligence processing right at the edge of our networks. Parallel to that is the drive for sustainable green computing, designing energy-efficient hardware to offset the environmental damage of the last few decades. When you understand the basic logic of the machine, the mystery behind the glass fades. You're no longer just pushing buttons on a black box. You're engaging with the actual mechanics that power our world.